So this is a great time to review exponential growth models. So this model works for both exponential growth and decay. Let's start with growth. So the base model that we'll use, P of t equals P sub 0 e to the kt. So let's talk about what all of these things are. So P sub 0, right, this is the amount present when t equals 0. So whenever it is you start, that's going to be right when you key off of how many you have. So K is called the growth or decay constant. If it's positive, T, it's growth. And if it's negative, it will be decay. And then T is going to be, let's see, I ran out of space. So T, time, and P of T, so our output, right, this is the amount present at any other time. So this is the model that I'm going to be using. You can, and a lot of times you'll see this variation on that model where P of t equals P sub 0 times B to the t. So it takes that E out, right? So remember, E is just our natural base, yada yada. So the relationship between the two, so B is equal to E to the K, and you can sort of convince yourself by raising both of these to the T, right? And you'll see that you get both of these guys here. So this is one way you could see the relationship. The other way you could see it is that K is equal to the natural log of B. Right, so all of these things here are related to each other. So I'm just going to be consistent, and I'm going to use the E to the KT model. So a lot of times when you see, right, this exponential growth or decay, the thing you'll be interested in, or you'll be asked about, is, well, what's the doubling time? How long does it take to have twice as much as you have now? So doubling time, this is how, so we're asking for when, so t equals what? How long does it take P of t to equal twice what you start with? Well, so now here's where it gets amazing and totally mind-boggling, is it doesn't matter how much you start with. Okay. So I'm going to go ahead, so I'm going to set P of t equal to 2p naught. So up here in my original equation, I'm going to have 2p naught equals p naught e to the kt, right? So the p naughts divide out. It doesn't matter. The doubling time is the same. So I was asking for t equals when, so let's go ahead and solve this for t. So to do that, right, we'd need a natural log. So natural log of both sides leads us to here, and then solving for t, the doubling time is the natural log of 2 over k. So again, going back, it doesn't matter what your initial amount is. So if you start with 10, the amount of time it takes to double, right, to get to 20, is the exact same amount of time that it would take to go from 100,000 to 200,000. So I have a formula, and I have a graph here. And where's my abbreviated graph? Here we go. So I'm just going to flash this up here. So this is the total number of COVID-19 cases in the U.S. between March 6th and April 6th. Okay, so that's all I've come up with. I don't know about you guys, but that looks like a perfect exponential curve. So I did a little computing, and where is my equation? Oh, here we go. So I came up with this model using a regression function. So on March 6th, the United States had 224 cases. So this is total cases. And when I did my model, my K value came out to be 0.2291. So I want you to keep in mind what is T going to stand for in this particular model, right? So my model comes from this set of data, March 6th to April 6th. And on March 6th, right, we had, so this is the number on March 6th. So T is going to be days since March 6th. So if this is the model, and it works pretty well for these dates, it starts to fall apart, which is good for dates after that. What is the doubling time going to be? So how long should it take us to go from 224 to, what is that, 448? So we could either do 448 and solve, or we say, well, the doubling time is equal to the natural log of 2 divided by k, which is 0.2291. Now my calculator really isn't showing up today very well, but I'll go ahead and do it and I'll tell you what I've got. So natural log of 2 divided by 0.2291. So 3. Think about that. 3 days, right? In the early days of this, or early-ish days of this, it was taking 3 days to double the number of new cases, right? And it didn't matter, right, if we had 224 or if we had 10,000. So let's think about that then. According to this model, when should we have passed, let's say, 1,000 cases, or let's say 10,000? So how long, so we'll add in a question here, how long to get to 10,000 total cases? Oh, am I writing today? So 10,000 equals 224 e to the 0.2291 t, and we're going to solve for t. So again, let's go ahead and do it. We'll divide both sides by 224. I didn't really leave myself space, so I'm going to just talk through some of this. All right, so divide by 224. And then we'll take the natural log, so I've got 10,000 divided by 224, natural log of that, and then divide by that k, 0.2291. 16 and a half days. So this comes out to t is about 16.6 days after March 6th. So March 22nd, March 23rd, somewhere in there. Okay, and then if this model would have continued, and it didn't, again, good thing, what would the total number of cases we would expect on April 22nd? Right, so the first thing you need to do is figure out, well, how many days is that since March 6th? So, right, we've got March 6th to April 6th. Is 31, and then from the 6th to the 22nd is another 16. So it looks like our time would be 47 days. Well, let's see. So then now we're just finding the p of 47. So that's going to be 224 e to the 0.2291 times 47. Oh, well, luckily, we didn't get, oh dear, I think I've lost a thing. Okay, no decimals yet. 1063165, I'll round 1. 10 million. We didn't get there, so that's good. So I'm going to go ahead and show you the other graphs that I've done. And I'm grabbing this data from Worldometer. I don't know if you guys have seen that one or not, but worldometer.com. Thank you very much. And you can see, so I have two scales here. That's why I wanted to show you this. I have two scales going. So the first one here is linear, and that means my y-axis is linear. It's the same step each time, so it's going up by 250,000. And you can see that we did not get to, right, on April 22nd, right, we're about in here, and that's still below, right, a million, which is great. So we did not reach, right, we didn't follow that model. Now I want to show you, so if you go on Worldometer, you can see up at the top, right, instead of linear, I could have done a logarithmic scale. And the logarithmic scale, that's affecting the y-axis, because for exponential growth, it gets too big too fast to see some of that early stuff that's happening. So it kind of turns that, it turns that exponential curve into a linear-ish curve when you plot it on a logarithmic scale. So when we look at that, you can sort of see, right, it's actually starting to look kind of logarithmic, which is good. We want it to flatten out. And this isn't the flattening out that, right, they say flatten out the curve. I don't think this is what they're talking about. But you can definitely see that somewhere in here, the slope of that line changes, which is great. So we could probably use that model that I came up with. It's probably better in this first part up through maybe the mid-20s of March. And then it looks like we're following a different model with a less robust growth constant. Okay, so this is not all about COVID. Exponential growth and decay also works for other fabulous stuff like radioactive decay. So half-life is something that you've probably heard about in a science class. And again, it is that same model. The only thing that's going to be different for us is that K will be negative. Half-life means how long until there's half as much. So at the Hanford Nuclear site down in central Washington, they deal with many radioactive substances. So I read an article this morning and I pulled 3 of the different radioactive isotopes that are present at Hanford. So the half-life for strontium-90 is 28.5 years. Iodine-131 is 8.040 days. And plutonium-239 is 24,110 years. So they can be all over the board. So if we know the half-life, so let's do this. If we know the half-life, can we find K? So let's find it for strontium-90 and for plutonium-239. So we know the half-life. We know how long it takes to get to half as much. So this time, right, these are the t values for when p of t equals half of p naught. So 1/2 p naught equals p naught e to the k times 28.5. So again, it doesn't matter what you start with. It takes the same amount of time to go down by half. So divide out your p naughts. So 1/2 equals e to the 28.5k. So for strontium, oh, you can tell the sun just came out. I'll switch to purple. For strontium, so I'm going to do the natural log again. So the natural log of 0.5 divided by that 28.5. For strontium, your K value is negative 0.02432. So your model, how much you have, P of T, is whatever you start with, e to the negative 0.02432 times t, where t is the number of years. Oh gosh, so let's pay attention to that. So since this time that I put in is in years, this t is also in years. You do need to pay attention to that. So if we did it for iodine 131, since our half-life is given in days, that T would also have to be in days. So this is in years. And the same thing will happen then for our plutonium 239. So 1/2 equals e to the 24,110 K. So K equals, and I'm doing a solid equals, it should be a squiggly because right at some point I'm going to start writing decimals. So K equals negative 2.875 times 10 to the negative 5. So P of T equals whatever you start with, e to the negative 0.00002875. T, where T is the years after you noticed P naught. Okay, so it's not only scary things, it works for money if you have something that's continuously compounding, or other non-viral population growths.